we had talked about like, what's the point of having inverse functions? And the point of having inverse functions is the same as the main point of having like square root functions or logarithmic functions. They let you undo functions that are more obviously obtainable. Plenty of things go at an exponential speed. Whenever you want to undo an exponential, you do logarithm. Similarly, we have lots of things that are modeled by like trig functions, anything that has to do with a triangle. Whenever you want to solve something that involves a triangle, you need an inverse trig function. Cool, let's see one very specific example right now. Hopefully that was all the way, so we'll kind of do that. Let's experiment with this. Let's try to solve this equation. Cosine of x equals 1 over. That's what we'll focus. Alright, so let's go through the standard list and start by counting how many solutions we expected. How many solutions do we expect? Just by looking at that graph, how many times does y equals 1 go across the graph of y equals cosine of x? 4 times in this picture, but if I kept on drawing this picture, how many would there be? They'll just keep happening. So that's already like a weird thing. Like, I don't know if we've experienced a situation where a function that we want to solve has infinitely many solutions yet. Well, I guess unless you count identities, but those are just solved by everything. Let's try to find it. And let's start with this. There's one obvious solution, one that inverse trigonometry tells you. So if you want to solve cosine of x equals 1 over 30, and you know inverse trig functions, tell me one angle whose cosine is 1 over 30. Ooh, well, let's go over what inverse trig functions do. If I tell you theta is the inverse cosine of some number of x, what does that mean? Yeah.
Isn't it like cosine of the angle equals x?
Nice. And we'll write what comes after the and in a moment, but let's put that down first. So, if I ask you for an angle whose cosine is 1 over 30, what's the first guess you should make? Well, I want like a 1 over 30 there. Let's try inverse cosine of 1 over 30. So whenever someone asks you to solve an equation that looks like cosine equals number, your first guess, and it's not even a guess, the first solution you write down is inverse cosine. So there's like one of the solutions. And let's get this also. What's the range of inverse cosine?
0 to 5.
0 to 5. So, this number, inverse cosine of 1 over 30, let's locate it on this graph. And on this graph, we see a bunch of solutions. I'll label them with A, B, C, and D because I want to do this multiple choice. Out of those 4 candidates, which one is inverse cosine is 1 over 30?
C.
C. Yeah, cool. Because it should be the one that's in between 0 and pi. Nice. So this one is cosine inverse of 1 over 30. And there are 2 different paths we can take from here. And maybe I'll just see what people want to do. So there's like one solution out of infinitely many. How could you find another input whose cosine is 1 over 30 given this one?
Add or subtract pi.
Cool, let's try it. I'm going to pull up the Desmos. was told at some point that this is like a generation independent but like old possum thing. Calling things by the name of the and then the name that they are. So saying things like I'm gonna go to the Aldi as opposed to Aldi. The Desmos. Y equals cosine of x. Y equals 1 over 3. So let's list the one we have so far. X equals arc cosine of 1 over 3. And maybe I'll even give that a name. Let's call that x0. Cool. Is that one of the x values where the graph of cosine crosses that horizontal line? Nice. And you said add pi?
Add to the cosine.
Cool. So like that?
Yeah.
Cool. Does that correspond to a solution? No, but like something. So why did you want to do add pi?
I was thinking like the period of the.
Yeah. Yeah, let's add the period of cosine to this. But what's the period of cosine? 2 pi. In fact, I could get more solutions by adding more 2 pi's. So, Desmos lets you do that. I'm going to build a list. So there's like a whole bunch of solutions, all separated by a multiple of 2 pi's. Have I captured all of the solutions? But I have infinitely many. That's something. I'm going to put those down. So, in order to find the rest of the solutions, well, what's the period of cosine? It's like an interval of like 2 pi. So if from 0 to, there's 2 pi. If I could find like the name for that solution, or equally well that solution, then I could add 2 pi to whatever that thing is and get more solutions. How could you describe those 2 points? Let's like think about some symmetries of the unit circle. Let's draw. There's a unit circle. On the unit circle is cosine the x value or the y value. Cosine is the x value. So I want cosine equal to 1 over 3. So let's draw a line of x equal to 1 over 3. And so far we've found this angle, because that's the one that's in between 0 and 2 pi. 0 and pi. I need to get this angle. How could you describe that angle out of the angle we started with? Negative would do? Nice. The other solution in the period, so maybe the one B is ambiguous here. To get another solution, let's use the identity that cosine of minus x is the same as x. So I just stick a negative sign in front of the solution that I found to get a new one. X1 equal to negative cosine inverse of 1 over 3. That feels pretty good. You'll notice here that what I did originally was like use 2 pi minus x. What second solution would you use if you use that instead? I guess you get 2 pi minus cosine inverse of 1 over 3. Let's check those two and see what they tell us. So let's see. X equals negative cosine, or cosine. All right. Does that give us another solution? Yeah, that's green line crosses the graph at one of the points where the blue line crosses the graph. So that's an x value of another solution. The other secondary solution we could have used is That give us another one? That gave us, well, it gave us that. Oh, nice. So now we found like infinitely many solutions, and then we found one additional solution. How can we find the rest of the solutions? Another round of plus 2 pi k. Nice. Plus 2 times pi times k. There we go. Cool. Does that seem to have captured all the solutions? Nice. So, once you know all the solutions that lie in a single period, I find all the solutions. So I found one solution and another. It doesn't matter which two solutions you find, as long as they're two like really distinct solutions. You can find all the solutions by taking this solution, cosine inverse of 1 over 30, adding 2 pi k, and negative cosine inverse of 1 over 30 and adding 2 pi k. Where k is an integer. And one thing I'll point out is if you were doing that, would you have gotten the same infinite family of solutions? Yeah, it just would have like shifted that k by 1. Neat. Does that feel pretty okay? So if you want to solve a trigonometric equation and find all of the solutions, start by finding one solution using inverse trig. Find another solution using inverse trig plus some symmetries of the trig function you're studying. Then add 2 pi k's. Cool. Feel pretty good? So let's, yeah, this is one more thing. So let's try to list these. So let's try to compute cosine inverse of 1 over 3 plus 2 pi k. Negative cosine inverse of 1 over 3 plus 2 pi k. And I think I want to distribute some just computer/calculator walk across the classroom. So, compute both of these when k equals 1 and minus 1, 0, 1, 2, 3. And let's just go left to right. Here you know what happens at k equals minus 1. K equals 0. K equals 2. K equals 3. Well, I didn't count right. K equals minus 2? Let's not match it there. So, I guess the first column is going to be cosine inverse of 1 over 30 minus 2 pi, and negative cosine inverse of 1 over 30 minus 2 pi. Once you get those decimal approximations, tell me what you get. Ooh, make sure you're in OEDM mode. You'll be able to tell because you'll get a number that doesn't look like it's in degrees. Once someone's got an entry to go on the table, tell me what you get. Ooh, how many people like don't see how to enter inverse trig functions on their calculator? Okay, cool. Then I won't like do the fancy thing of pulling up the TI-84 simulator online and doing it myself. All right. Inverse cosine 1 over 30 minus 2 pi. What do you get?
Negative 5.05.
Cool. And what about when it's negative cosine inverse of negative 1 over 3 minus 2 pi?
I got negative 7.51.
Cool. Let's keep going left to right. Inverse cosine 1 over 3. Cool. That was for negative inverse cosine 1 over 3? Cool. And I guess that means inverse cosine of 1 over 3 is just that without the negative sign. Neat. K equals 1. Tell me the two numbers. I guess it'll just be an extra plus 2 pi, right? So what do you get out of that? So I'm going to need cosine inverse of 1 over 3 plus 2 pi times 1, so plus 2 pi. Nice. And now minus 2 pi. Probably be negative. Oh, no. The minus is here, it's not there. Yeah.
5.05.
Oh, neat. It looks like there's some like symmetry there. I guess that makes sense since cosine is even. K equals 2.
12.7.
And negative inverse cosine plus 2 pi times 2.
11.34.
Cool. And let's see. This is the question I'm walking towards. Let's just try to look at this count and see how many of these things are in between 0 and 4 pi. Open parentheses there. How big is 4 pi? 12-ish. So we'll see if we have some edge cases that we need more precision with that. That looks like it's in. That looks like it may or may not be. Maybe we have to we can think about it for a little bit. So right here, this should be cosine inverse of 1 over 3 plus 4 pi, I guess. Oh, so actually just by looking at that form, is that bigger than 4 pi? That's 4 pi plus a bit. So I think we have enough here to count how many of these live in that interval. So let's just list them. Is that in between 0 and 4 pi? In between 0 and 4 pi? In between 0 and 4 pi? One. So far. In between 0 and 4 pi? In between 0 and 4 pi? In between 0 and 4 pi? In between 0 and 4 pi. Oh, cool. So how many solutions does this look like there should be in that interval? 4. And let's just also graph this and see if that looks correct. How many periods of cosine is 0 to 4 pi? 2. So let's write cosine over 2 periods. There's one full period. There's a second. There's y equals 1 over 3. Oh, cool. Does that look right? Oh, nice. And maybe I should open circle there, close dot there, because I want that. Cool. That feel pretty good. How different do you think this process is going to be for sine instead of cosine? I think not much, but a little. This step, the step 2, I think will be different because that actually has to do with what cosine is. Let's try to do that. Sine equals 1 over 30. So there's the line y equals 1 over 30. Again, we expect infinitely many solutions. What's the false solution you should expect?
Inverse sine of 1 over 30.
Nice. So, we can add 2 pi k. There's infinitely many solutions, and that's like half of all of the solutions. And to get a second solution, let's think about the behavior of things on the unit cycle. I want sine equals 1 over 30. Sine is the y value on the unit cycle. So far we found like that solution. I want that solution. How do you get that second solution? I guess we can't think of like the numeric thing, like what's the symmetry of the cycle that's happening?
Reflection over the y-axis.
Reflection over the y-axis. And I don't know, I guess like, there's the angle that is the initial solution. To get this new solution, well, I guess I want to go over by pi, and then back by whatever this number is. Oh, cool. So how do you do that?
Subtracting from pi.
Yeah, you do pi minus the thing you were arguing. So second solution, pi minus the false solution. Plus 2 pi k. Cool, now you found all the solutions. So, in general, does this seem basically like an algorithm? Yeah, I think so. There are some subtleties that I'll put in this little step-by-step guide that'll go through the algorithm. If you want to solve an equation that looks like cosine equals a number, well, I guess first let's deal with like the weird cases. So let's suppose I ask you to solve like cosine of x is equal to 53. What would you tell me?
Cosine can't be that big.
Cosine can't be that big. So if this number is just too extreme, then there are no solutions. And same for sine. Alright, cosine and sine can actually be equal to plus or minus 1. So let's try to do that. Going to do these, let's just do it real quick by just drawing a picture. So suppose I wanted to solve the equation cosine of x equals 1. So I guess there's an x value of 1. So I want like all the angles that describe that x value on the unit circle. What are they?
2 pi k.
Yeah. There's only one infinite family, there's 0. And so you can add 2 pi k. 0 plus 2 pi k gets you back to 2 pi k. And then again and again. What if I give you x equals negative 1 to solve? What looks like the false solution to find? Pi? Is that like the only solution you see on the unit circle? Ooh, what are the others?
Pi plus 2 pi k.
Yeah, so you see like only one point on the unit circle that does the job. Once you get that one point, you say, ah, well that means I found the only one on the unit circle, that's going to be just given by 2 pi k terms. Same thing for sine. If I want to solve sine equals 1, that means I need to think about y equals 1. Again, it looks like there's only one point on the unit circle that does that. What is that angle?
Pi into 2.
Cool. What if I want it to be negative 1?
Pi over 2.
I'm going to give myself space, because there's another thing you could write. There are people who rather write minus pi over 2 plus 2 pi k. Would that also be correct? Yeah, good. It doesn't matter which like your starting solution is. So I guess what's the point there? Before you start like following this general algorithm, ask yourself also, are there actually just no solutions? Ask yourself if it's like one of these weird values of plus or minus one. And I don't know, I don't think you need to memorize what I just threw out. You just need to remember, oh, I can try the units off and read off the angles. Great, do that. In the general case, let's write down the thing we got. So the simplest solution was cosine inverse of whatever that number is, or sine inverse of whatever that number is. Well, let's remember that we can simplify some of these. Like, what if that number c were 1/2? What's the inverse cosine of a half? Looking at your unit circle if you need. How many people want to know a first off how to compute inverse trig functions by looking at the unit circle? Yeah, let's do that. Alright, so if you want to compute cosine inverse of 1/2, let's see, cosine is the x value, right? So if I want inverse cosine, I want to start with the x value and then you tell me which angle you get. So if you start with the x value and then give me the angle, what do you got? Pi over 3. So pi over 3 is the inverse cosine of 1/2. So simplify if possible. Let's do the same thing for sine. Looking at your unit circle, or this unit circle if you don't have yours on yet. What's the inverse sine of 1/2? Pi over 6, because you insert the y value because that's sine. Read off the angle. Nice. Once you get one solution, then you can get infinitely many solutions by adding 2 pi k's. Now you can get a second solution. And let's see, for cosine, how did we get a second solution? Yeah, you use basically that. Cosine is even. So once an even function does something once, it's going to do it on exactly the opposite x value. So negative cosine inverse of c plus 2 pi. How do we get the second solution for sine?
Subtract the original solution from pi.
Nice. And then you can add 2 pi k's. And as always, like, as you go through, try to check for simplifications you can make in any particular example. So let's say you solve an equation that has to do with sine or cosine equal to a number. Do you think we can do something similar for tangent? Right, we have an inverse tangent function. In fact, like, compared to sine and cosine, tangent of x is way better behaved. And so solving an equation that involves inverse tangent is going to be like 2 lines. So let's try to do that. There's the graph of tangent of x, and the line at y equals c. Step 1, give me the simplest possible solution. So I guess that'll be that solution. Oh, sorry. What's the simplest solution you can think of to tangent of x equals c?
Inverse tangent of c.
Great, just inverse tangent. And since inverse tangent has domain, range, negative pi over 2 to pi over 2. That's the point you'll find. Cool, that feel pretty good? Now I think we can do something similar than we could with sine and cosine. What's the period of tangent? Period of tangent is just pi. Notice that's the same as the length of the integral we used to involve. So if I just take that and move it over by pi, I'll get another solution. If I do it again, I'll get another solution. If I move it back by pi, I'll get another solution. Oh cool, that looks like it gives all the solutions. Nice, if you want to solve it, an equation involving tangent of x equals a number. It's just inverse tangent of whatever that number is, plus pi k, while I'm going to simplify. For example, negative root 3. Tell me, what is the inverse tangent of negative root 3? Negative root 3.
Negative pi.
Cool. You would start by saying I want tangent to be negative root 3. That corresponds to an angle of pi over 3. Negative pi over 3. Cool. That feel pretty good? Alright, so let's solve 2, just to practice with this idea of doing some simplification. Let's solve tangent of x equals root 3 by following exactly this algorithm. So, I guess step 1, find the simplest solution. What's the simplest solution to tangent of x equals root 3?
Inverse tangent of root 3.
Cool. Simplify if possible. Is that something you see on your unit circle? What angle is that?
Pi over 3.
Yeah, cool. There might be some instances when maybe I ask you to do this while walking in degrees. So let's also do this in degrees, just to also think that way. How many degrees is pi over 3 radians? Yeah. So there's like the initial starting solution. Pi over 3 radians are 60 degrees. And now we use the fact that we know the period of tangent. So now we're going to try all the solutions. In radians, what's the infinite family of solutions to this equation?
Pi over 3 plus pi k.
Pi over 3. The starting solution plus pi k. And let's write that in degrees too, just for the sake of doing it also in degrees. Or 60 degrees plus. How many degrees is pi radians?
180.
Or 60 degrees plus 180 degrees times k, where k is allowed to be any integer. Nice. That feel pretty good? Alright. Solve for me sine of x equals negative 1 over 2. to have and start. Check that you've simplified it as much as possible. See if that's a number you see on the unit circle. And compare answers with neighbors and see how things look. Cool. Let's start going to the plan. So I think I'm going to do the opposite thing and flip back to the previous page so you like see the algorithm later. So let's see. I want to set it equal to negative a thought and solve. So that puts me in not that weird case. Not that weird case, not weird case. So I'm in the normal case. So step one is the simplest solution, just inverse sine of whatever that number is. Now simplify. What angle do you see whose sine is negative 1 over 2?
Negative 5 or 6.
I hear negative pi over 6. Do I hear agreement? Cool. Oh, cool. So that gives me half of the infinite solution. Pi over 6. Negative pi over 6 plus 2 pi k. Ooh, let's see. How many people instead used as their false solution 11 pi over 6? Nice. Does it give you the same infinite family? Nice. Yeah, so, right, it's convenient that you like have a standard name for it coming from inverse trigonometry, but if it's an angle you just know, it doesn't matter whether you use the one that inverse trig gives you. You'll just have a family of solutions that shifted by a little bit. Let's find the second solution. Either by looking at the unit circle, or by like doing the same manipulation as is in that table. What's a second solution to sine equals negative 1 over 2?
Pi minus whatever your answer is.
Nice. Pi minus x0 is the standard way to get it. So I guess in this case it's pi minus pi over 6, which simplifies to
7 over 6.
Yeah, that feel pretty good. And people, how does their second solution like negative pi over 6, negative 5 pi over 6 instead? Oh cool, give you the same infinite family? Yeah, so you can have different looking infinite families. In fact, if you get a solution and someone else does, just see if the like representatives of your solutions differ from 2 pi by 2 pi's from each other. Cool. That feel pretty good? Anyone instead decided that they wanted to find their solution in degrees instead of radians? Yeah, okay. I guess it would not have been objectively wrong to because the problem didn't specify. But usually I'm going to want radians instead of degrees unless I specifically say I want degrees. When I do specifically say I want degrees, you better make sure you're in degree mode. Lots of people on the exam lost like some silly points because they like forgot to check if their calculator was walking in radians and or degrees. But did all the right walk, but then got like final answers that were like not believable. Which happens. Especially in like the time setting of an exam, on like homework, or if you were doing like some important application, you better make sure that your units line up correctly. Otherwise you get that apocryphal story about NASA in the 90s accidentally building a satellite that absolutely could not launch because some of their units were in metric and some of them were in imperial and like nothing would come together. I don't know if that's actually true, but it's a fun story to say. Anyway, let's not go one step beyond that, right? The point of inverse trig is it lets you solve things that looks like trig function equals number. Well, you can be more complicated than that. What if we want to solve something that looks like function applied to trig function equals null? So I combine some trig functions together and do some algebra and ask you to solve that. Like, I don't know. Here's one. Let's find all the solutions to 3 times the sine of x plus 2 equals 1. That seemed like a doable thing to solve. Maybe I'll see how people feel with 6 minutes on the clock. Would people rather they do or would people rather I do? Should I be talking? Cool, then I will. Those of you who are doing it on your own will probably get an answer faster than I did. So I think here's a plan. Step 1, the first goal I think is just going to be to turn this into sine of x equals a number. Because then I can use like the stuff we've done so far today to solve it. So I guess that means I want to solve for sine of x. So if you take that equation and I say get sine of x on its own, what's a good first step? Well, how about minus 2? Subtract 2 from both sides. Now you get 3 sine of x equals negative 1, I think. All right. Next one. Divided by 3, giving me sine of x equals negative 1 over 3. Oh, cool. That's exactly the type of solution that we've been talking at length about how to solve. So now that we have an equation that looks like that, what's like the first solution you see?
Sine inverse of negative 1 over 3.
Cool. If you look at your unit circle, is that a y value you see on the unit circle? No, so I can't like use the unit circle to simplify. You can use a calculator to get a decimal approximation. Maybe I'll propose one simplification you can do. I see a negative inside of those parentheses. Can I do anything with that negative sign? I guess I'm asking, is inverse sign even or odd or anything like that? So what can I do with that negative sign? And that might not seem like a major simplification, and it's not, but it's just as many keystrokes if you want to just type it in as a form. But something nice will happen in the next step. How do you get the second solution if you know the force?
Pi minus the first solution.
Pi minus the first solution, so you'll do pi minus sine inverse of 1 over 3. Oh, cool, that's pi plus sine inverse of 1 over 3. That looks a little simpler than it otherwise would have. And now we can write down the full solution. Full solution. X equals minus sine inverse of 1 over 3 plus 2 pi, okay? Or x equals pi plus sine inverse of 1 over 30 plus 2 pi. Okay. Cool. That feel pretty good? And let's take a tour through the rest of this packet. The only thing that will get more complicated from here on in this packet is combining these ideas with algebra you already know. Does that next equation look just as hard to solve as the one we just did? Nice. No more complication there. That kind is technically easier because tangent's easier. Oh, how about that? Is that like an equation you could do? What seems like the starting point to like begin the process? Okay, now.
Substitution.
Yeah, what do you want to substitute? Yeah, and maybe I'll substitute it for the letter S, so I don't know that it's sign. Doesn't matter what letter you use. Oh, cool. That looks like it's easy to solve. So you'll wind up sine x equals this, or sine x equals something else. Oh, now you have two simple trig equations to solve. That one was just as difficult? And you can start combining things together. What if you have like mixed trig equations where some sines and some cosines happen? Surely you can still do something. We'll see what we can. And at the most complicated, we'll see something that has a tan squared and a secant squared. So, with that, I think I'm going to be some stopping point. We will see you all tomorrow. Yeah. And then certainly yeah, maybe check out the schedule, right? Yes. Here is my example. Thanksgiving should at least be kind of better. Even if like the 20th on Wednesday. So like, if you like shut down a little bit over the local, that's fine. When you come back on that Monday, like look back at the phone. Or just get them all going down like, what do you do? Oh, yeah.
Mason. I have mine too, please. Carson.